Hello again. So we're going to do initial rates to determine order, and there's a couple really complex ones on here. I'm going to solve them a couple of different ways. Number 1 through 3 is fairly straightforward like you've seen before, but 4, 5, 6 are a teeny bit more complicated. So let's go ahead and do the easy ones first, and then we'll do the hard ones. Alright, so in this reaction, you want to determine the rate law, basic stuff where you're using the table logic. So between the first and second trial, that one's constant, this one is times by 2, which you can see that it's also, the rate is also times by 2. So chlorine is in first order, diatomic chlorine. And the second trial to third trial, you'll see that the chlorine is constant and that the nitrogen monoxide is multiplied by 2. And if you do this, 1.45, you always take the larger rate divided by the smaller rate. That's going to say, this is meters per second, I'm sorry, molarity per second. That's going to be 4. And so that means that 2 to some power will give us 4, meaning that x is equal to 2. So we have second order here. The rate law, therefore, is rate is equal to K times the concentration of NO squared times the concentration of chlorine to the first. So that's for part A. For part B, what is the rate law constant? Be sure to include units. That's always very important. So use the first data point, trial 1, molarity per second equals to K times 0.10 molar to the second times 0.10 molar to the first. When you divide by 0.10 molar squared times 0.10 molar to the first on both sides, once you divide that, you're going to get 180. Ooh, can't see that. 180 per molarity squared per minute. In this one, the rate, if you look at the initial rate given to you in the table, it's not per second, it's per minute. So please be sure that you're watching your units for the data information given to you in the problem. All right, number 2. The reaction is studied. Here's the information. Yada yada. Okay, so we know the rate law is going to be rate equals K times something. All right, let's go do table logic again. So using the information given, this one's a teeny bit harder because you have one that you can find very easily, and then the second one you're going to find, but then have to account for some changes that were made in the trials additionally. So let's work through this one. 1.1 or 0.18 and 0.18 is constant. Between here and here, you see that the reaction is decreasing by half. But I'm going to show you that I want to make this a little bit more directional. Meaning that from trial 2 to trial 1, you're multiplying concentration by 2. From trial 2 to trial 1, what's happening to the concentration? I think it's easier to think about these in whole numbers versus fractions. So that one is also being multiplied by 2 for between the second trial to the first trial. So that means that iodine is in first order, as 2 is equal to 2 in this case. 2 to the first power is equal to 2. After that, you have to find where another one is constant. Well, you can actually do, you can do it this way or this way. So keeping this constant, and you see that from trial 3 to trial 4, what has happened to the concentration? That's being multiplied by 8. If you go from trial 3 to trial 4, take the larger one, that's the 7.91 times 10 to the negative second, divided by the smaller one, 0.988 times 10 to the negative third, you're going to get also 8. I did that in my calculator because I did it a different way and I just saw the constants were the same there. Okay, so between these two, 8 times greater means the rate increases by 8 times. Also means that we have our hypochlorite that is first order. So our rate law is I minus to the first times OCl minus to the first. All right, what's the rate law? And then we can go look at the units just right now. We'll see it's molarity per second. That's our normal stuff. So let's stick with that. Using the first data trial, 7.91 times 10 to the negative 2. Molarity per second is equal to K times 0.12 molar times 0.18 molar. Both these to the first power. And notice that your molarity squared is on the right. You have just molarity on the left, so you've got to have molarity in the denominator of K. That answer is 3.66 per molarity seconds. Next one. Using this reaction to determine the rate law. So let's look at our constants here. This one seems pretty easy. Hydroxide stays the same between first and second trial. ClO2 doubles. What happens to the rate? So if you need to, on the side of your paper, say 5.7 times 10 to the negative 2 divided by, oops, did it the wrong way. Larger one, 2.3 times 10 to the negative 1 divided by 5.75 times 10 to the negative 2. Look at that really closely and you'll notice that the OCl2, well, since it's multiplying by 2, it's causing the rate to be 4 times greater. That means that we are in second order here. So 2 to some number is 4. Now we have to change leave the ClO2 constant and change the hydroxide. So here's where the second and third trials where the OCl2 is constant. And I'm going to go directionally like I did previously. So from trial 4 to trial 3, we're multiplying by 2. And then from trial 4 to 3, you'll see that 1.15 times 2 is equal to 2.3, so that means the rate is being times by 2 as well. So since the concentration of OH minus is multiplied by 2 and it also doubles the rate, that is going to be first order. So I think sometimes it's nice to not do halvesies stuff so you can have whole numbers to work with. The rate law for this one is K times ClO2 to the second power times OH minus to the first power. Notice the rate law constant. Plug it in, 5.75 times 10 to the negative 2 molarity per second is equal to K times 0.050 molarity squared times 0.100 molarity to the first. When you divide by your proper units and you see that you've got molarity cubed on the right and molarity on the left, you need to have molarity squared in the denominator. I'm going to write this one slightly different. 230 molarity to the negative 2 times seconds to the negative 1. That's the same thing as saying that they are in the denominator, so you will normally actually probably see this written because people don't like to put slashes when they're typing stuff out. Alright, here's the big dog. So I'm going to show you how we can do some of this with table logic, and then for the ones that we just cannot figure out because of the complexity of the problem or because more than one thing is changing in a specific data table, more than one concentration, then we have to use something called logs. You should know about logs, but if the log ratio of the rate ratio is equal to x times the log of the concentration ratio, if you divide by the log of the concentration ratio on both sides, you get x, and that's what we want to solve for because that is the order of interest. So in number 4, I started off with table logic, and then I had to end up using logs. So between trial 1 and 2, B and C are constant, A is times by 2. What happens to the rate? You can see that 0.0304 divided by 0.0076 is equal to 4. Therefore, A is in second order because doubling it causes quadrupling the rate. Okay, and you've got to go with a different concentration of a different reactant. So between A, let's see here, where do I go next? Between trial 1 and 3, both A and B are constant, and trial 1 and 3, C is times by 2. What happens to the rate? So if you do over to the side of your paper, 0.0076 and divided by other way around, 0.0107 divided by 0.0076, you should get some number which we cannot determine because it's not a whole number. So hold off on part C because that's going to be the logarithmic solution that we're going to need to implement. So moving back, let's go to B, the concentration of B, and see how it changes. So between trials 1 and 4, B is being multiplied by 2, while A is staying constant and C is staying constant. So I'm trying to use different colors so you can differentiate between these. Between trial 1 and 4, the rate is being times by 2, so 0.0076 times 2 is 0.0152, leaving us with B being first order. Okay, so now let's go implement the logs for the concentration of C and determine its own order. The way you do this is, I'm going to scroll down, is you're going to say the log of the rate ratio over the log of the concentration ratio equals X, which is our order. Between trial 3 and 1, you'll see that C is that was where we got stuck, where C is not a whole number, so we can't put that into the order right now. And it doesn't make sense because there's going to be some more information I'm going to give you here. So plug in your information for the trial 3 and trial 1. So the information given to you is 0.0107 molarity per second. That's right here, a trial 3, divided by the smaller number, 0.0076 molarity per second for trial 1, which is up there on the table. So that information you're replicating, but using concentrations of C in this denominator here. So log times the concentration of C in trial 3, which is 2.0 molar, divided by the concentration of C in the first one, which is 1 molar. Whatever you get here is your order for C. So sometimes instead of trying to troubleshoot through a table logic, it's easier just to plug it into the logs as long as you're using the appropriate trials, which will be the trial where you are seeing a change in C and no changes in the other two reacting concentrations. So this is called half order. So when we write out the rate law, you'll see that rate equals K A squared B to the first and C to the 1/2. Overall order of 3.5 or 3.5. Okay, so that was all for number 4. For number 5, given the hypothetical data, determine the order of reaction for H plus I plus J equals K. So it's a similar situation. You'll notice that we can maybe do 1 or 2 of the rate constants of the orders. So between trial 1 and 3, H and I are constant, where J is being multiplied by 4. What happens to the rate? And you have 2.7 over 1.7. That doesn't really make a whole number, so I'm going to go ahead and implement the logarithmic information. So this first one is for number 4. The second one is going to be for number 5. So you have to choose the appropriate trial. So I'm going to go ahead and do J first because that's the one I already have chosen to be inquiring about. And then we're going to go back and do H and I. So between trial 1 and trial 3, you're going to be able to use this information. So order will be log of trial 3 data, 2.7 molar per second, over trial 1 data, which is 1.7 molarity per second, divided by the concentration ratio, which is 4.0 molar for trial 3 and 1.0 molar for trial 1. This gives us 0.333. Interesting. So we have 1/3 order. So I told you we could have fractional stuff. I guess you didn't know that would be this much, but we do have fractional information. Okay, so now let's go ahead and find some trials where 2 are constant and 1 is changing. Between trial 1 and 2, you'll see that J, I, and I are constant and H is changing. So for H, we're going to do information between trial 1 and trial 2. So you guys have this in front of you. Log of 3.9, 91, molarity per second over 1.7 molarity per second. So this is comparing trials 2 and 1, divided by the ratio of the concentrations, which in trial 2 is 2.3 molar, divided 1.0 molar in trial 1. So that information I got from right here in the table. Okie dokie. So once you solve for H, plug this information in your calculator appropriately, and you'll get 1 for that order. So that's the order for H. For I, we got to do one more. So we need to look and see where I is changing and nothing else is changing. Going back to the data table, you might look for a minute before I continue. Okay, so notice between 4 and 1, H is constant. That's good. Between 4 and 1, J is timesing by 2. That might be a problem. We'll look and see what happens. Between I and trial 1 and 4, it's going from 1 to 1.8, so we're going to have to implement the log. And then I'll show you how we use the J order in order to account for the I order that we're going to calculate. Okay, so we're using information between trial 4 and trial 1. So, log of the larger one over the smaller one, where we have 6.94 molar per second divided by 1.7 molar per second divided by log of 1.8 molar, which was trial 4 data, divided by 1 molar, which was trial 1 data. This gives us 2.39. Okay, so in this case, we have to account for the fact that J is also changing. If J is also changing, what you do is you take the sum of I and J, which is 2.39, minus J's order. This is just one method. Minus J's order, which was 0.333. That gives us about 2. That leaves us with the I order all by itself. Alright, so in the end, we have rate equals K times H to the first, I to the second, and J to the 1/3. Alright, last one. 6. Given the hypothetical data, determine the order of reaction. I'm going to go ahead and go straight to determining all of these through logarithmic information. So for R, we need to find where R is changing and nothing else is changing. Between trial 1 and 3, R is changing, Q and P are not, so we're going to go trial 3 versus trial 1. So the log of 0.0274 molarity per second divided by 0.0365 molarity per second divided by the concentration ratio of log of 0.75 molar divided by 1.0 molar. So this is the concentration of R that has been changing. Once you solve for this, you're going to get 0.996, which you can round to 1. So that's the order of R. Then you're going to do another one for P or Q. I'm going to go ahead and do Q next. So the ratio needs to be through a trial that's got only Q changing, if we can find one, and R and P are not. So that's going to be trial 1 and 2, 1 and 2, 1 and 2. You'll see that Q is changing, R and P are not. So I'm choosing 2 to go on top because it's got a larger rate, 1.47 over 0.0365. molarity per second, molarity per second, divided by the log of the concentration ratio, which is 0.35. So that looks like a 6 actually. 635 over 1.0 molar. You'll notice that all these units are being canceling this entire time because orders have no units. So once you calculate this in your calculator, you get 1.99, which you can go ahead and round to 2. All right, so R was first order, Q was second order. P is a little bit more difficult. So if you're looking and looking and looking, you're going to find that there are no situations between trials where Q and R are constant and P is the only one that's changing. It's just not there. So we have to utilize some complex thinking here. If you compare trials 4 and trial 1, all of the concentrations are changing for all of the reactants. But we're going to look at P and only P and then make some adjustments. So the log of the larger number, which was 1.85 molarities per second, divided by 0.0365 molarities per second, divided by the log of 1.9 molar, which is in the fourth trial, divided by 1.0 molar, which was in the first trial. All right, once we get this, this is 6.1. But you'll notice that there are some changes being made for R and for Q. This is not the order. So R, the ratio of the concentrations of R between trial 4 versus trial 1 is that you've got R concentration going from 2.3 to 1.0, comparing 4 to 1. Q's concentration is going 4.7, sorry, from 1 molar to 4.7 molar. Since we already know these orders, we can plug this into our log concentration ratio, or just notice that from trial 1 to trial 4, this is being multiplied by 2.3, and from trial 1 to trial 4, this is being multiplied by 4.7. We're going to take both of these numbers and plug them into the rate law to show that P has not done anything to the rate, and it's actually going to end up being zero order, but I'm going to show you anyway. Okay, so looking at the information for trial 1 to 4, the rate goes from here to here. If you take 1.85 and divide it by 0.0365, we're going to see that this number, whatever this gives us, is equal to what we will get when we plug information in. So let's take that rate of the first trial and multiply by the concentration changes with their orders of Q and R. So 0.0365 is what we want. 0.0365 molarity per second is the initial rate. Take this and multiply by what Q would do to a reaction. In this case, Q has been multiplied by 4.7 times, and we already found that Q is of second order, so I'm going to put a 2 right there. Then we also found that R was already, 2.3 times increased. We found that it was first order. Whenever you multiply the initial rate by the changes that would occur from the concentration changes of Q and R, you find that that number is 1.85 molarity per second. This is what the rate should be if only R and Q had some impact on the rate. This is also so happens to be the trial 4 rate. So logically we should say, okay, since Q and R are the only ones that are changing, and actually P is changing as well, but Q and R changing causes the trial 4 rate to be what it says in the table. So we look back at the table, that is what it says in the table. That means that P has no impact whatsoever on the rate, and that Q and R are doing all the work. Meaning that P is zero order. That's a lot of work and a lot of talking to just say it's zero order. But you have to prove it to yourself or prove it to people in the AP exam. Most of the time you won't have something quite this hard, but I want to make sure you're professionals. So the rate law is as follows. Zero order in P, second order in Q, and first order in R. All right, and you do not have to do number 7. Thank you very much.